There are times when logarithms can be useful for making graphs of numbers that vary over a large range from each other. So I'll just show you a couple of examples. And these are inspired by things in the book. But so you can go and have a look there if you like, if you happen to have the book. So first of all, let's look at an exponential decay. So here's our normal graph. And let's say we've got something going down from 1,000 over time. The units aren't very important here. So if it's an exponential decay, then the graph will look like that. But then if we take the logarithms, so take the logarithms of these numbers, then 1,000 would become 3, because we're in base 10. And then the logarithms, we're doing it in such that the logarithms are evenly spaced out. And so in this case, the graph would be transformed, so we've got a nice straight line. So it's not a curve, it's a nice straight line. So this is easier to deal with. For example, if you're trying to interpolate numbers. From it. That's an exponential decay. And similarly, if we've got exponential growth of bacteria, so we've got an exponential phase of growth and then a plateau. So this is what we did in the labs recently. So here we've got bacteria over time. So this will be time here, probably. So here we've got a count of bacteria, and so if we're letting them grow, then it goes up slowly, and then we've got this. So that we'd call it, well, so we want to know exactly where the logarithmic phases of growth would be. So it's clear that we've got a plateau here. So if we transform that into logarithms, then you'd get a graph that looks something like this. Then it's easier to see that this is the logarithmic phase growth, and this is the plateau, stationary phase. So in this case, logarithms are good to assess stages of growth of bacteria and where the log phase would be. So those are some ways that logarithmic and exponential functions are useful to us, and transforming between normal numbers and logs on a graph can help us see our data more clearly.